14, we were trying to find the pressure in the atmosphere. Right, and then we came up with a density function for the density of air. Density of air, what was that? 1.30 minus something times 10 to the minus 5h, right?
1.6 times 10 to the negative 1.
And then we're trying to find the height at the h is 28,000 feet. Now we're trying to find the density, the pressure of the air and the top of Mount Everest, right? So remember we had used this equation, P is P atmosphere minus density of air, GH. And if we use the constant density of air, we got negative pressure. So that means it doesn't work. So now we use the differential form of this. Truly speaking, this only holds true if the density is constant. The differential form of this is P minus P atmosphere is negative dHg delta H, we can call this. And then this is delta P. Right? And then now we change it into the differential. dP is equal to negative density of air GdH. So incremental change in pressure, a very small incremental change in pressure, is negative the density of air G times the small incremental change of the height as you're going up. Now when the density of the air is constant, then this turns into this, right? But when it's not constant, then you have to integrate it. Now you integrate this from pressure P of atmosphere to P at some point. So visually speaking, what are we doing here? This is the pressure of the sea level, and this is equal to P atmosphere. We're calling that P of the P atmosphere at the sea level, right? So now we want to find, let's say here's a mountain or any place, right? We want to find the pressure here. So we're saying, what's the meaning of the dP? The dP is the loss in pressure when you go up by a certain incremental height dH. So dP will give you the change of pressure from here to here, right? The P of sea level, right? To some incremental height above that. So let's call that P of H, you know. So if this is the ground pressure there, if I go up slightly, what's the pressure there, right? That's what that means. So now I'm integrating all the way from the pressure of the atmosphere all the way to the pressure at some height, right? And that's equal to negative the density of the air, G dH, from 0, which is the ground level, to some height H, see? And so now when the density of the air is non-constant, I can put whatever function it's equal to, right? And then the integral here will just give you P minus P atmosphere, sea level. And then you're going to have here negative integral 0 to H. Then you're going to put the density of the air dH, right? Then you can integrate this. So now the integral of this will be P minus, the P atmosphere I can put as 1.15 times 10 to the 5th, right? And then you get minus 1.30H is the integral of this, right? Then I can distribute the negative inside. And then when you distribute the negative there, you get a positive, right? Then the integral of this is what? 1.6 times 10 to the minus 5, H squared over 2. Then I evaluate that from 0 to H. Then when you put H, you just get H. When you put H, you get H. When you put 0, you get 0. So it just basically eliminates and you just get that. So it's a definite integral. I don't need to add a constant here. Now I can put my height, right? So what is my height? 28,000 feet, and then we change that to meters. right? So 28,000 divided by 3.281. .98 meters, right? So it's pretty much like 8,534 meters, very close to 34 meters. So we can go from 0 to the height, which is 8,534. So now I can put that height into this 8,534 plus 1.6 times 10 to the minus 5 over 2, and then you're going to have here 8,534 squared. Okay, so now I'll put that all in and then add this to that side, right? And you get the pressure. That will give you the pressure at the top of Mount Everest.
You forget G right here.
Oh, did I forget G? Yeah, there should be a G. That's important. So 9.8. Again, whenever I make a mistake, it's on purpose, remember? Yeah, it's so to show you what not to do, right? So then I have a G here, 9.8, and I have a 9.8, 9.8, 9.8. By the way, G is also changing as you go up, right? G is also variable.
So,
and just like we learned in chapter 13, gravity decreases.
Yeah.
But do I have to take that into account? Or is the change of the G from the surface of the Earth to the top of Mount Everest negligible?
Negligible.
Oh, it's very negligible.
so it's like,
Right? Because imagine the equation for G is Gm over the distance of the object from the center of the Earth, right? So if this is the Earth, and then you got a mountain that looks like a dot, basically. Right? So does the G change a lot from here to here? For general relativity, it does. They've actually had an atomic clock at the top of the mountain and at the bottom of the mountain, and they measure the tiny bit difference that the clock runs at the top of the mountain. But you know how small that is? Like a nanosecond. And they prove general relativity from that. That clocks run at a different rate. But for our purposes, the drop in G is so negligible, like 9.8, maybe 0.0000, you know, whatever. So very, very small. So for this, you don't need to take that into account. Okay, so put that all in. Let's see what we get. So what is that?
Oh, no, I was just handing it to you. I thought you forgot it.
I like that. That's good. He's giving me work to do. Here's the calculator. You can do it. That's a good one. Try doing that next Wednesday on the test. Oh, by the way, the test will start, what, 10:15. I give you an hour and 45 minutes. So next door, there's no class before there's class. So we're gonna start over there. 10:15, be there sharp. We go from 10:15 to 12 o'clock. I would have done it here, but there's a class after ours. After we get the answer, then we'll analyze it and see if it makes sense. Okay, anything?
1.18 times 10 to the fifth.
1.18
times 10 to the fifth.
It should be less though.
Oh, I messed up. There, I forgot a 9.8.
Oh, yeah.
Yeah.
Yeah, exactly. Which is why, if I had forgotten the 9.8, I would have caught the error, right? Then I would have looked at my answer and I said, oh, it doesn't make sense, right? So you have to get the 9.8, multiply it. You get a negative pressure?
Yeah.
Again?
Yeah.
That's odd. Because we checked to see if the density was negative, but it wasn't, right? We did this equation. You get a negative?
Yeah, I get negative 4,500. It's because of the air density, the equation you used.
Negative 1,513.
That's what I got.
So even though the density of the air is not negative, the pressure drops to negative. That's what that's saying. Pressure already drops to negative. Because I made sure that when I put H is 8,500, that I made sure that this density of the air is not negative. Let's see here what happens. This is negative. Did I maybe make a mistake with the signs? Should this be positive, or is the signs right? So how do you make sense? In other words, how do you make sense of this differential that you set up, and whether or not the differential itself is not wrong. Should I have a positive there? Should I integrate from 0 to h? Should I integrate maybe from p to pc level? You see what I mean? So you want to make sure your error is not because of this or is something you're doing wrong. So should I be integrating from p of the ground to the p? The way I would do that is to say, okay, if delta h is positive, if dh is positive, what do I expect dp to be?
Negative.
Right, so in other words, if I'm going up in height, I expect the pressure to drop. So dp I expect to be negative.
Yes.
So if dh is positive, dp I expect negative. So I don't see a problem with the negative there. Then I go over here and I look at my limits. 0 to h, okay, that's going to give you positive there. Okay, does this give you negative? If you integrate from p atmosphere to p of the pressure at some height. So then that gives you pressure at some height minus pressure of atmosphere. Yeah, I do expect the pressure at a certain height to be less than the pressure of sea level. So this is negative. And this is also negative because I expect 0 to h to be positive. So I do expect that to be negative. So my integral is right and my limits are right. So that means there's something with this function that it's predicting if the density drops this much, by the time you get to the top of the mountain, the pressure is already negative. So that means this function should be even less, like maybe 10 to the minus 6, or maybe something like this. 9 times 4 times 10 to the minus 6, then it might work. Now, the problem could also word it to you differently. What if the problem said this? The pressure of the sea level is 1 atmosphere, and the pressure when you go to the top of Mount Everest, because you can easily Google this, and you can say, okay, what's the pressure at the top of the Mount Everest? And then you can see Google, and then let's say you find out that the pressure there is 0.82 atmospheres. Now, can I work backwards and say, the problem can say, the density decreases linearly, 1.30 minus alpha h, find the alpha constant that you need in order for this to happen. We can work backwards, you see. So we can do the same procedure and then say P minus P atmosphere, but this is already given, right? So 0.82 of the P atmosphere minus this. Now, this is going to be alpha, right? And now I can say negative 1.30 H 9.8 plus alpha H squared over 2 9.8. So find the alpha that's required in order to make that work out. You see? So here it's going to be alpha. 8534 squared 2. So it's the same equation. Here I'm going to have, I can factor out this number here, 1.015 times 10 to the 5th, 0.82 minus 1. Right? And now I can solve for alpha. So what would I do? Calculate that, take this back to that side, divide all by this, and then we'll get what the alpha constant needs to be. I think that way is better because you're not going to get any negatives or weird answers. You're basically working off of the data that you get from the internet, and then you work backwards to calculate what density function we should use. So let's see what we get. .82 minus 1, that's 0.18, right? 2.53 times 10 to the minus 4. Yeah. What was I using for my for the constant?
1.6 times 10 to the negative 5.
Oh, so it needs to be a bigger number.
Well, I have a thought. I don't know if you can plug in. It's like using that function, row air, 1.3 minus alpha, each plug it into P right here, and then do it directly without taking the integral.
No, this is density.
Yeah, that's density. To see that density, plug it into the row. Plug it into the P pressure function
Without integrating?
without integrating.
You can't not integrate. Why? How could you not integrate? The pressure there is 0.8 atmosphere. This is an integral problem because the density is variable. Yeah.
With that alpha, you get negative rho.
Oh, you still get a negative rho, right?
Negative 0.86.
Yeah, if I put 85, then you get a negative. It's not working out, right? So now this comes out negative density. Negative density, negative something, right? What is it?
0.86.
Zero.
Huh?
0.86.
Oh.
I feel like it's a little bit.
So that means, given this data, given the height of the Mount Everest, it can't be a linearly decreasing function. It's got to be some other. The density of the atmosphere has to be another kind of decreasing function. Most likely, exponentially decreasing.
Because when I plug it in, I got a
Linearly decreasing is just not fitting the data.
I plug it into that function, I get a positive, right? Like, which is.
I'm not sure what you're plugging in. How could you do that without integrating?
Like,
What are you plugging in here?
into the pressure function, like P is equal to P atmosphere minus that function times G times
It's an
H.
integral. You can't plug it into here because this is a variable function. Are you plugging in here 0.82 P atmosphere, and then you're plugging this equation into here, and you're solving for H, right? Is that what you're doing? You're
Yeah.
plugging this into here, you're putting here 0.82, and then you're putting H is 8,000, right? Can't do that. It's cheating.
I mean,
You're trying to make the problem easy by not integrating, but you can't.
I didn't plug in 0.82 right here. I just plug in like atmosphere minus rho GH, which is the formula right here, like the pressure formula. Atmosphere minus rho GH.
Mhm.
Rho is, since rho is changing and H is changing, so this is two, like, you mean like two variables, but since rho is influenced by H, to see that?
Okay.
So on different level it has different rho, it has different density, but H is okay, like, because it's the only variables in that function, which is like 8,834. When you plug it into that, that function, rho is changing, right? Rho, you get a value for the rho, and you get a value for the H. That's why I use that function too.
Okay, I'm trying to see what you did. So you're saying you did rho of R, so you're saying you did 1.3 minus what's alpha, and then you put 8.5 something.
H is H, just use H right here.
Okay, then what you do?
And then you plug into the pressure function, which you make it quadratic.
This one?
Yeah.
Okay. Plug this into here.
Yeah.
Now I want to see, because if we don't want to just say something is wrong, we want to see why it's wrong, or maybe he's not wrong. Okay, so now you're plugging this here.
Yes. And then that's a quadratic, right? You see that pressure
Yes. Okay. Okay.
in respect to H is a quadratic function.
So then multiply this in.
I mean, like, that looks simple, but I don't know, like.
Okay.
why
Then
they-
what?
And then, like, since like it used to be, alpha used to be like 1.6 times 10 to the negative 5. That's the first
The
variable.
old alpha, yeah. But let's just say we don't know alpha.
So plug in like 8,834.
To A, to
Yeah,
H.
to H.
And then here plug in 0.82.
Not like 0.82. Like, how do we know like 0.82?
Let's say we looked it up online and it told us the pressure at the top of Mount
yeah, and
Everest.
then let's solve like alpha or solve.
Yeah, I see what you mean. So 8534. Then you solve for alpha. And then what do you get? You did it that way?
Yeah.
So he's basically doing, does his equation look same as mine?